All right, this is the second hour of Physics 1B for December 3rd. What are we on here? December 13th. Okay, so we were just talking about interference. We did a little bit of a sidetrack into the history of the theory of light, largely because I think it helps you to understand what's going on with this interference idea. So again, we're thinking about something like this, where you have two different sources, maybe of sound waves, without all the extra particles. And we're trying to understand how these patterns are produced. And really what we're interested now in is figuring out where are these dark spots going to occur and where are the bright spots going to occur. Or in the case of sound, the loud and the silent. Yeah. So imagine we have the following situation. We have two speakers. There's a speaker here that's producing sound, a speaker down here that's also producing sound. And we're going to say that, let's assume that each one of them is producing sound of just one frequency, okay? So these could both be tied up to the same sound generator, and they're both producing sound with the same frequency. This is important to make this work out. So now, if we go to some position, let's say, for example, right here, and let's say that it's exactly the same distance for each of them. So we draw a line from this one out to here, and we draw a line from this one out to that same location, right? And let's say that we call those R1 and R2, okay? Each of these is going to represent the path length that's traveled by our wave from this location to the point here, which we could call P maybe. Now, if R2 minus R1, absolute value, happens to be equal to 0, then this is going to lead to constructive interference. And the reason why is because if each of these waves is producing sound of the same frequency, and each one starts off, let's say, at the same kind of point in its wave cycle, and it gets to, this is so hard to draw. So this thing goes up, and so we got a wave, sound wave coming in here. Oh my god, I really apologize. I don't know how to do this, drawing at an angle, a wave thing. So we've got a wave coming in like this, and say it gets to there like that. We've got the same wave from the bottom, because they have the same frequency, coming in like this. And so if they arrive and they're in sync with each other, right, so they both hit maximum at the same time, then that will only occur if the path difference is 0, okay? This is going to be constructive interference. This is where you get two maxima at the same time. This is like a bright spot in those pictures that we saw, okay? If they're equal to 0. But if we were to take the bottom speaker and we were to move it backwards exactly one wavelength, let's say the wavelength of this sound is 0.5 meter, okay? And we move this back exactly one wavelength, so we put our source right here, right? If it's exactly one wavelength behind, such that it goes through exactly one wave cycle before starting over again right here, right? So if this is exactly one wavelength, so if the speaker was instead over here and not here, and there was a one wavelength difference in these path lengths, you would still get a maximum because the wave cycle repeats itself, right? So that means that you get constructive interference if the path difference, R2 minus R1, is equal to 0, or lambda, or 2 lambda, etc., right? Basically, put in a more general way, you get constructive interference if the path difference is equal to a whole number multiple of lambda, where lambda is the wavelength of the wave, and n can be equal to 0, 1, 2, 3, etc. Do you all understand that? Does anyone have any questions about why that would be the case? That if the path difference is exactly a whole number multiple of the wavelength, you're gonna get constructive interference at that point. Let me know if you have any questions about that. Is that clear enough? I really want to know, because I don't want to keep going. If you don't understand this part, you're not going to understand the next part. So does that make sense? Why that's the condition to get constructive interference? All right, it's because the waves are kind of in sync with each other. They match up. That's exactly right, Troy. The two waves, each of them is coming in at the same time. They're both waving like this, right? And if they both get to the same point and they're both doing the same thing, they're synchronized, right? Maybe that's a better way of putting it. Instead of saying constructive interference, the two waves at that location are synchronized, right? When it's the max only or the same point. I guess what I'm trying to say is that, and maybe even writing the word maximum here is the wrong word to write, because really what we're trying to say is the two waves are synchronized at that point, right? They're synchronized, which means they're not interfering with each other, right? When one wave is on the up cycle and hitting a crest, the other wave is doing the same thing. When both waves go down, they both do the same thing. They're both doing this at exactly the same time at that location, right? So if we were to look at P, we're not getting any interference. There's not a point when one wave is up and one wave is down, right? They're both going to be in sync with each other. Now, the other possibility, if you want to get destructive interference, yeah, I'm not talking about pressure. This is just a point in space. Okay, so now the other possibility is if R2 minus R1. Now, if they're out of phase, right? If they're out of phase, that means that one wave has to be, they basically have to be doing this. One wave is going up and down like this, and the other wave is doing the opposite. So they kind of they're doing this kind of thing, where one wave is up and the other wave's down, and when the other wave reaches its maximum, the other one's at a minimum. So they're out of phase with each other. And the only way you can have that for perfect destructive interference is if the path difference is half of a wavelength. Okay, I'll try to draw a picture for this, but the way to write that is if the path difference is n plus 1/2 multiple of the wavelength, where n again is going to be equal to 0, 1, 2, 3, etc., any integer multiple, then this is going to be destructive interference. Because now the waves are basically canceling each other out, pretty much. Okay. Okay, does this concept of interference of waves make sense? So let's do an example. So here we have loudspeaker interference. By the way, let's say one other thing about this. You should not expect that you can test this at home, and here's why. So, for example, in front of my TV, I have two speakers, and if I go sit exactly whatever distance away, but I'm right in between them, and the two speakers were producing exactly the same sound, the theory would say that I would hear louder sound here. Okay, constructive interference, the idea would be that it would be louder. Like, that's kind of what this means. This means louder. And destructive interference means quieter. Okay? Or maybe no sound at all. If it's pure destructive interference, it could be no sound at all, right? But can you go to your home and can you take two speakers, get both of them just producing a single test sound or something like that, stand at a location and hear a louder sound, and then maybe move off to the left to some position here and hear a quieter sound? And the answer is no, because in a room where speakers are producing sounds, those sounds reflect off of the walls, and the reflection off of the walls prevents this from occurring. You have to have these things only producing sound and have the sound waves themselves uninterrupted. So you'd have to be like out in a field or in a large gymnasium or something like that. I've definitely seen demos of this. I'm not trying to say that this doesn't happen. I'm trying to say that, like, it's not going to happen in your home. I've seen demos of this at, like, science museums, I guess, kind of like when I was a kid or something like that, I think, where you can produce this, but it's just hard to do. It's way easier. It's way easier to do this with light than it is to do it with sound. So just putting that out there is, you know, if you go home and try this yourself and it doesn't occur, there's a reason for it. Because of the reflection off walls. All right, loudspeaker interference. We have two loudspeakers, A and B, and they're driven by the same amplifier and emit pure sinusoidal waves that are in phase. For what frequencies does constructive interference occur at point P? All right, so here's our setup. Let's draw this with the actual line so it looks somewhat reasonable. So So we've got two speakers, and they're separated by some distance. And we're looking at a point P, which is over here. So 1 by 2, so we need to divide this in thirds, something like that, right there. Okay, and this is 1 meter, 2 meter, 4 meter. Okay, so the question is, for what frequencies does constructive interference occur at point P? Okay, let's label this as R1. Let's label this as R2. Our speakers are here and here. They're producing sound. And we want to figure out what frequencies do you get constructive interference at point P. To get constructive interference, what we said was that if we take R1 minus R2, we take the absolute value, that this should be equal to, in order to get constructive interference, you need to have this be equal to 0 or lambda or 2 lambda, etc. Or just in general, we said n times lambda. So we'll just put in here n lambda. Whole number multiples of the wavelength. And in this case, we know what R2 and R1 are, and we kind of want to solve for lambda, but really what we want is frequency, and we know that V is equal to lambda times F. So that means that we can replace lambda here with V over F, so we can write this as R1 minus R2 equal to NV divided by the frequency. We can then solve for frequency. And then we can figure out what frequencies we're going to get constructive interference for. So N is, oh, we don't know what N is. That's going to be part of our answer. Velocity. At the very bottom of this, it says the speed of sound is 350. We're going to use that. So we multiply by 350. Divide by R1 minus R2. Okay, in our picture here, R1 is going to be 4 squared plus 1 squared square root. Minus R2 is going to be 4 squared plus 2 squared. We absolute value that because I think that the second term is bigger. And we get that the frequency should be equal to, tell me what you, yeah, you tell me what you get because I left my phone in the other room. Oh no, I didn't, it's right here. Anyway, tell me what you got either way. I got like 1,000. Do you all agree? Yeah, 1002.7 is also what I got. So it's N times 100, we'll call it 1003 hertz, which means that for frequencies that are equal to, well, a frequency of 0 doesn't mean anything, so that doesn't work. This is 1003 hertz. Also, that's too many zeros. And then you'd also get it at 2006 hertz. You'd also have constructive interference for 3009 hertz, I guess. And interval multiples thereof. But notice that like there's only particular frequencies that you're going to get constructive interference for. It probably doesn't massively alter the sound that you hear at this location. Okay. And then the question part B says, for what frequencies do you get destructive interference? So for destructive interference, the formula, we can skip a lot of the steps for this one. For destructive interference, the formula is just R1 minus R2 absolute equal to n plus half of lambda. So we can basically go through exactly the same derivation and then just replace, like the answer itself is going to be exactly the same, except, come on, let me just click. What is it? Why is this thing so... There must be a reason. What is the thing that allows me to click and create a cursor? I don't understand what it is. Anyway, so it's going to be the exact same answer, but now we just replace this with n plus half. So now we're going to get frequencies that are going to be like this divided by 2, which would be, what, 501.5 hertz? And then we would do 3/2 of that, which would be 15045, and then just, it's basically 101,504.5 hertz, and so on and so forth. You can figure out the rest of them. Okay, and so that's a little interference with sound waves thing. Anyone have any questions? Okay. I think now we're going to jump over to talking about the Doppler effect. How much time do we have left? Plenty of time. I want to say one other thing before we go on. Can n be negative? Not if you get negative wavelength, because wavelength can't be negative and frequency can't be negative. So I don't think so. I think it just is the ones that I said. It's 0, 1, 2, 3. It's positive integers. Is 0 an integer? Probably. Positive integers. For constructive, as long as it's a whole integer and the frequency is positive. Yeah, I guess so. Positive x direction. I don't think it should depend on direction. I mean, we're talking about numbers here. We're not talking about... for constructive interference, can n be negative? Can this be equal to negative lambda? I don't know what that would mean, because we're forcing everything to be positive by taking an absolute value here, right? So no, n can't be negative. Unless you can think of an example, Christian. I'm old and stuck in my ways. I can't see it. So if you can think of an example, let me know. Okay. I do want to say one other thing, though, about this story I was telling you about the history of the study of light and trying to understand what light is. So it turns out that in I think it's 97, maybe 1899, sometime around that time. You know, Christian, sometimes when you're struggling and then you solve it by doing something that doesn't make a lot of sense relative to the equation, it's probably because you have made a mistake somewhere in the calculation, and by putting that negative sign in, you're fixing that mistake, right? So if you then assume, because of that this n thing can suddenly become negative, then you're kind of you've basically gotten to the wrong conclusion because like the error you made has now been fixed by making a second error. You know what I mean? Does that make any sense? Since two negatives make a positive, if you had a minus sign error somewhere else in the problem and then it got fixed by making n negative, that doesn't mean n can be negative. Does that make sense? I made those mistakes a lot when I was studying too, where I couldn't get a problem to work out, and so then I I would change the sign of something and it would make it right, and then I would go ask my teacher a very similar question to the one you're asking, so I totally understand why you're asking. But don't let your own mistakes make you believe that should change anything, is what I'm trying to say. It should just be a reason to go back. When you get something that doesn't make sense like that, with this negative value for something that's only supposed to be positive, then you should go back and check. And I guess part of what I'm asking now is, were you talking about a problem that was like this, or were you talking about a problem that was from a previous chapter on like standing waves? I'll let you think about that. Anyway, okay, getting back to what I was saying. We were talking about interference of sound waves. We said that Newton said it was a particle, Huygens said it was a wave, then Young said, no, it has to be a wave, because how do you explain this? And then someone comes along and performs an experiment. I can't remember what his name is. Nowadays we refer to it as the photoelectric effect. Basically, it's the idea that if you shine light on a piece of metal, you can get it to kick off electrons and produce electricity. It's pretty much the idea behind the way a solar panel works. And the problem with this new experiment was that the wave theory of light didn't work anymore. The wave theory of light no longer explained the behavior of light hitting a piece of silver and then kicking off electrons. And the reason why it didn't explain it, you can learn more about in 1D. But basically what they figured out was that it was only particular frequencies of light that actually kicked off these photons. And if you're below a certain threshold frequency, that it didn't matter how bright you made the light, there was no way to get it to kick off photons. And it was a really surprising effect because they really thought that the energy of a light wave was related to its amplitude and not its frequency. And they figured out that the energy actually is proportional to frequency, and one of the ways that you can explain the photoelectric effect is to treat light as a particle. And that's exactly what Einstein did in 1905. He wrote a paper to explain what happens in the photoelectric effect, and in this paper, he basically said that light was a particle. So now you have Newton says light's a particle, Einstein says light's a particle, and this dude you've never heard of before, Huygens, says that light is a wave. So who are you going to believe? Are you going to believe Newton and Einstein, or are you going to believe Huygens? And the answer is you have to believe both of them, because in some situations you have to think of light as a wave. In some situations you have to think of light as a particle, and it turns out it's both, which is kind of what some people had said previously. And I think that's because I think you all have heard of this in modern like science stuff. You kind of know that nowadays we think that light is a particle and a wave. I still like to think it's just a wave, because what is a particle? We're learning more and more that we don't really know what particles are, and things that are particles actually exhibit wave properties. And one final thing to say about this interference thing, which is one of the most interesting things in the history of science, is that eventually someone got around and they tried the experiment that I just described to you, right? Where we were saying that, we were looking at this, right? And I asked you, what would this look like if we had particles, right? And you all agreed that if it was particles, that you get these two bright spots here, right? And that's true. If we shot baseballs on this side through some barriers, let's say we had a pitching machine over here, and the pitching machine was shooting out baseballs, well, that pitching machine would produce two spots of baseballs over here, basically, right? Well, eventually someone decided to do the experiment with things that they almost were certain were particles, which are electrons. Okay? So they produced the same experiment. This experiment was done by a group, two people, Davison and Germer were the leaders of this experiment. They passed a beam of electrons through a crystal. The crystal acts basically like these partitions. And lo and behold, these things that they thought were particles actually produced an interference pattern. And so did they then think that electrons were particles? No. They went back and did exactly what happened after the Young experiment. If electrons exhibit interference, they must be waves, right? So it turns out that everything is waves. And we just kind of use particles as a way to help us understand things, because we have a lot of experience with particles, right? We're really good at understanding balls bouncing off of walls. We understand what happens if, like, I take a ball and I throw it to you. You know what that experience is like of the ball flying through the air, of this hard object. But at the core, at the very core, particles are just a kind of way that we understand things, and everything is really waves. Everything. All right, so let's talk about the Doppler effect. And this will be the last thing we talk about this semester, probably, unless we have a little bit of time left at the end, and then we'll go back. Okay, so the Doppler effect I'm going to show you on here with this video, which means I need to switch my thing so you can hear the audio, because this is all about audio. So what I want you to think about is anytime you've been standing on the side of the road and you've heard a car go by, or you've heard an ambulance go by, or you've heard really anything that makes noise drive by you. I notice, like, every time I leave my house to go to get in my car is almost always parked across the street. So I walk up to the street and I hear cars pass me by. And every single day I notice this effect. As a car comes towards you, the sound that the car is producing, and what I mean is any sound it's producing, if it's honking its horn or just the sound of the rubber as it hits the road, cars make noise, right? As the car approaches you, it's going to make a very high-pitched sound relative to what happens when it passes you. The moment that it passes you, the sound of the car is going to dip in pitch. It's going to go from high-pitched on the way in to low-pitched on the way out. Is that something you all have experienced before? If you haven't, the next time you're standing on the road, see if you can hear this effect. It's really, really obvious. As long as your ears are relatively sensitive to pitch. I know that not everybody has the same like ability to hear different frequencies and stuff like that and to distinguish between them. But this is a pretty substantial one. So we're not gonna watch this whole video because a lot of the video is kind of garbage. But we want to just like hear what the Doppler effect is. The Doppler effect is that when something is approaching you, it sounds higher pitched than when it passes you, and it also sounds higher pitched the sound that's actually being produced by the object. So let's see if we can hear it in this video. If you can't hear the video, let me know. If you can, then don't worry about it. Okay, I had to mute my mic because it's playing through my speakers. But could you all hear that sound? It's important to understand that the sound that the train is producing is not changing. That would be a natural thing to assume, right? There'd be nothing wrong with that assumption. One assumption that you could use to explain this is, oh, well, right when the train passed me, the pitch of the sound just went down. But then you'd have to explain why it sounds that way every single time. Does the train just happen to turn its sound down every single time that it passes you? No, of course not. Let's listen to it one more time. I'm going to mute my mic. So just listen for the sound as it comes in, and then right when it passes, and try to note the moment that it passes you, because you really hear the sound change. Okay, so everyone can hear it? Understand what the Doppler effect is? So to define it in like words, the Doppler effect is the relative, it's the change in frequency of it could be any wave. This happens with light waves and with sound waves. It happens with water waves too. So it happens with any kind of wave. I'll give you an example with water waves. That's pretty easy to understand, I think. Change in frequency of a wave due to relative motion between the source of the waves and the observer. Oh, shoot. No, that's not. You know, usually when I'm writing, I will just look over to see what you're typing. And this time I was like, I'm just going to finish what I'm writing. I don't know why I did that. I should have looked. Okay, here we go. So the Doppler effect, the change in frequency of a wave due to the relative motion between the source and the observer. That's what the Doppler effect is. Okay. And your book goes through some derivations, and we could do the derivations, but we're not going to today because I want to do a few problems to make sure you understand how this thing is used. So the way that we're going to look at this is this. Suppose that we have the following scenario. Actually, let me give you an example to help you understand why this occurs first, and then we'll do it. Okay, suppose that I'm in a boat, right? I'm sitting here in a boat, riding along the water. And let's say that another boat comes along and they're traveling in this direction here on the water, right? So they're kind of going horizontal or perpendicular to the direction that I'm going. So I'm sitting here in my boat. And of course, when another boat comes by, its wake will produce waves, right? And so now these waves come along here. And these are just water waves, right? They come along here. And let's say that so this is the direction of these water waves. That's the velocity. So as these waves hit my boat, what's the boat going to do? The boat's going to basically do this. It's going to go up and down. Every time the wave passes by, it's going to go up a little bit and then down, and then up a little bit and then down. Okay? And let's say that the rate at which these waves is hitting me, it's hitting me at a frequency that's equal to, let's say, 3 waves per second, or 3 hertz. Okay? So one wave hits me every third of a second. 3 waves hit me every second, basically, right? All right. So now we're going to call this the frequency of the source here. This is the frequency of the waves that are basically produced here by this boat passing by. Okay. So now what I want you to think about is what would happen to the frequency that you observe. Okay, we're going to call this FO. This is going to be observer, and this is going to be source here, okay? So O stands for observer. We'll just put OBS, observer. The frequency that you observe, what's going to happen to it if the boat goes into the waves? Okay, so what if my boat is going in this direction? If the boat travels this way, is the frequency that you observe going to be greater than, equal to, or less than 3 hertz? If you move towards it. Are you going to get more waves per second or less waves per second if you move towards it? It's going to be greater, right? It makes sense, right? Because if you go this way, the waves are just, what was the effect of the waves on the boat? The effect of the wave on the boat was the boat did this, right? Every time a wave comes by, it goes up, but then it goes down. And it goes up, but then it goes down. You start going into the waves, you're going to go up and down faster. If you go fast enough, actually, you'll probably get on top of the waves and you won't even really notice it. But the reality is that you're going to be feeling more waves per second. And vice versa, if you go away, you're still going to probably get hit by the waves, but the frequency is going to be less. So let's turn this into an equation for ourselves. So suppose that I have a person here, and they're riding on a skateboard, and they're going in this direction. This is going to be my observer, O. So they have a velocity that I'm going to call V sub O, all right? And then over here, let's say that we have a car, and this is going to be my source, S. So this is the source. And the car is blaring its horn, maybe telling this skateboarder to get out of the way. Now the car is traveling along a road in the same direction in a line as the observer, and we're going to give it a velocity that I'm going to call V sub S. One other thing here we're going to need is the velocity of the waves here, which we're going to call V. Okay, so V is going to correspond to, let me write this a little bit above this. So V in this problem is going to correspond to the velocity of sound. Those are the waves that we're looking at. So similar to our boat example, this observer is going to hear a higher frequency than is being produced by the source. We're going to say that the source here is producing waves that have a frequency that we're going to call F sub S. Okay? And the question is, what is the frequency that is observed by this person here? And the answer is that it's going to be equal to, let's see if I can remember how this is done. I'm going to give you a different equation from your textbook because I really don't like the equation in your textbook. And I kind of like it, but I don't really understand the way they set it up. F sub S. There we go. So that's the equation. I'm sorry, I just want to make sure, because I want to make sure that I'm giving you the same equation that I gave my other class. It looks like the same equation, right? V plus VO over V minus VS, okay. because I'm kind of doing this without notes, and this is one place where we're kind of deviating from the book. So here is the Doppler effect equation. And I have to tell you some things about it. VO and VS, because they're velocities, they can be positive or negative, right? So these are the sign conventions. When the objects are approaching each other, VO is positive, VS is positive, okay? So VO is positive when... Oh man, I'm so tired of writing on this tablet. Positive when approaching the source. And it's going to be negative when, what's the word? Moving away or receding from the source. We'll just say moving away. It's probably easier to understand. Okay. And VS, which is the velocity of the source, is going to be positive when approaching the observer or moving towards the observer. And then it's negative otherwise. As far as I can tell, the equations that your book gives, it looks like the same equation. No, it's not. Their equation is the same, except they use maybe their equation is better. I don't know. This is just the way that I learned it. So this is the way I'm going to teach it to you. Their equation has a positive sign in the denominator, and they define VS to be, they basically reverse these definitions. And I don't like that. To me, this is just easier to understand mathematically. We'll look at some examples, and maybe we'll talk about this, why I like this equation better. But they do say the same thing. It's just the way they define the positive and negative is really hard for me to understand. So for me, positive is just when you move toward the source, you get positive. When you move toward the observer, you get positive as well. It's just the way that I do it. If you want to use the equation in the book, go for it. It just has a slightly different positive-negative definition. I can see what the confusion is, because for me here, this number would be positive and this would be positive, even though this is going backwards. But that's not a problem for me. Maybe it's a problem for some physics textbooks, but not for me. Okay, so let's look at some examples. Does anyone have any questions about the Doppler effect before we start going? I guess I could say some general things about it. So why is the Doppler effect? Why do we care about it? Well, interestingly enough, the Doppler effect can tell us something about relative motion, as we will see in the last problem that we're going to do. So when we want to know something about the direction something's going and how fast it's going, the Doppler effect can give us information about that. So places where this is used are in the radar gun when a cop is trying to guess your speed, and they use a radar gun to speed you. What do they call that? To zap you? I don't know. What happens is that a beam of light goes out, it hits your car, it reflects off of your car, and it comes back, and there's a change in frequency, and that change in frequency can get converted into a speed, and that's how the radar gun detects your speed. Doppler effect is also used in detecting storms. I think probably some of you have heard the term Doppler radar before. Have you all heard that before? Doppler radar? I know where I'm from in Oklahoma, we got tons of storms, and every time there was a big storm, if you're sitting there watching television or something, there would be a big notification that would come up, and it would tell you there's a storm in your area, and they would cut to a meteorologist, and he'd have all these plots of, oh, the storm's coming in this direction. You can use the Doppler effect to track a storm. That's why they call it Doppler radar. In the same way a cop uses a radar gun to detect your speed. You can figure out how fast the clouds are moving and stuff like that. The speed of sound, yeah, v equals lambda f still applies to that, Troy. That's right. Where else is the Doppler effect used? It's also used in astronomy, very heavily used in astronomy, as a way to detect the speed of a galaxy relative to us. So when we look at distant galaxies, if the galaxy is moving away from us, its frequency is going to be shifted downwards. And in terms of light, when the frequency goes down, we call that a redshift, because light has frequencies that range from red up to blue. And the frequency for light is like the color. You know, in sound, frequency is pitch. In light, frequency and color are the same thing. So when we look at a distant galaxy, when it moves away from us, its light gets shifted over to the red, so the galaxy appears to be slightly redder. Now, it doesn't actually appear redder to our eyes, but what we can see is when we take the light from the galaxy, which most of it's being produced in stars, which is mostly helium and hydrogen, that light has a certain signature to it. In the same way that you have a signature that you write on documents, light has a certain signature when it comes from certain elements, and so we know what that light should look like. When you pass that light through a spectrometer, it looks a certain way, and when it's moving away from us, the way that that light moves shifts over. The lines that it produces shift over to the red, and we call that a redshift. When a galaxy is moving towards us, then the light gets a higher frequency, according to the Doppler effect. Just like when the train comes towards you, you hear a higher frequency. And we see it as a blue shift. Interestingly enough, scientists named, can the denominator ever be zero? Like if the velocity of the source is the same as the velocity of sound? That's what you're saying? Interesting. I hadn't really thought about that. That's a good question. We're not going to look at any problems like that, but we will talk about what happens when you move faster than the speed of sound. If you want, we can talk about that. That's where you get a shock wave or a sonic boom. Anyway, going back to Edwin Hubble. So I guess an example of that, Donald, would be, say you're sitting on the ground and a jet plane flies over your head and breaks the sound barrier, so it travels faster than the speed of light. Faster than the speed of sound. Then a sonic boom occurs. And I don't know what that means in terms of what you hear, because if this object is traveling faster than the speed of sound, then the sound that it's producing probably isn't going to reach you. I don't know. Oof, okay, getting a little. I need to focus. We'll come back to that at the end, Donald. We'll talk about things moving faster than the speed of sound, which would be what would happen down here. All right. Okay, so Hubble, he's looking out at the galaxies. He's plotting all these different galaxies, right? He's looking at all of their different redshifts, using the redshift, the amount by which the light frequency is changed, to then go back and convert their velocity, which is like, we'll do this in the last problem we do. If you know what the shift is, if you know what the observed frequency is, and you know what this frequency is supposed to be, then you can figure out the velocity of the source. And that's what Hubble's doing. He's figuring out how fast all these galaxies are moving. And he finds out that every single one of them, except for the ones that are really, really close to us, all have redshifts. And the ones that are farther away from us have even bigger redshifts, which means they're moving even faster. So what he determines is galaxies that are pretty close to us, they can have random velocities. Go a little bit farther away, they're all going away from us. Go even farther away, they're going farther away from us, and they're going even faster. So what he determines from all of this is that the universe itself must be expanding. The only way that an observer could look out in the universe and see that all of the different galaxies are all moving away is either that we're in the center of the universe, which is an absurd thought, or that space itself is getting larger over time. And that's something we know because of the Doppler effect and because of the experiments that were performed by Hubble, where he measured how much of a Doppler effect occurred for different different galaxies. And nowadays, redshift is the way that we measure. It's actually the way that we measure distance in space, because we know that redshift is proportional to velocity, and velocity happens to be related to distance. That means that you can use the amount by which the light is redshifted from a galaxy to figure out how far away it is. How amazing is that? Just by looking at the way the light changes of an object that could be billions of light years away from us, right? Just by looking at detailed ideas about how that light changes, understanding the Doppler effect, we can determine not only how far away it is, but also how fast it's going. And it's billions of light years away from us, and we can still figure that information out. Isn't that amazing? And it's at the core of modern astronomy in terms of how we observe the universe, is this thing called the Doppler effect and this idea of redshift. So let's look at some of the math. I think these Doppler effect problems are pretty easy, actually. They can be kind of confusing, but once you've done a few of them, they're really not that hard. So let's look at a few examples. A police's car. How much time do I have left? I want to do all of these. Some of them are kind of easy. Okay, I think we have enough time. A police's car siren emits a sinusoidal wave with a frequency of 300 hertz. Okay, so here we go. We've got a police car, and it has its siren, and it's emitting waves Fs equal to 300 hertz. Okay, the speed of sound is 340 meters per second, and the air is still. So the velocity of sound is 340 meters per second. Part A says, find the wavelength of the waves if the siren is at rest. Well, that's pretty easy to do, because if the siren's at rest, then the wavelength of the waves, we could just use velocity of sound. Oops, I didn't mean to do this. This shouldn't be Vs, my bad. Just V. Okay, that's the velocity of sound. Source and sound, it gets kind of confusing, I guess. All right, we want to find wavelength. We can use V equal to lambda times the frequency. This is the frequency of the source. We're looking for the wavelength of the source. The wavelength of the source is going to be equal to V over Fs. So that is going to be 340 divided by the frequency that we're given of 300. So we get 1.13. Okay, part B says, find the wavelength of the waves in front of and behind the siren if it is moving at 30 meters per second. So now for this part, our same object, okay, let's do part B over here. So now there's two possibilities. One is going to be, all right, our car is moving this way. It has a speed of 30 meters per second. And we've still got a siren. It's still producing waves. We want to figure out the wavelength of the waves in front of and behind the siren, okay? So we'll do front first. In front of the siren, if someone is standing right here, and this person, which we're going to call the observer, VO, is at rest, the question is, what is the observed wavelength? We're first going to figure out the observed frequency, and then we're going to figure out the observed wavelength. This person is going to observe a frequency, FO, that's equal to the velocity of sound plus the velocity of the observer divided by the velocity of sound minus the velocity of the source times the frequency of the source. Now, in this case, the velocity of the observer is 0, but V is the velocity of sound, so we put 340 divided by V is 340 minus V source is 30 and then we multiply by the frequency of the source, which is 300. And this will give us not the wavelength, but the frequency observed. So the observed frequency then, when the car is moving towards, is 340 divided by... So I get 329. And of course, we can then convert that into wavelength by taking the V over F. So we take the velocity of sound, divide by the frequency of the frequency observed. So we get 340 divided by observed frequency of 329. And this gives us the observed wavelength, which is going to be 1.03 meters. So slightly less than it was. Wait. Should it be bigger? No, smaller. It should be smaller. Yeah, that's right. This is 329, this is 300. Never mind. All right, that's the observed frequency when the car is going towards the observer. Any questions about that? All right, second possibility is same car. It's going this way. And now our observer is going to be over here. Again, VO is going to be equal to 0. So the only difference now is that VS is moving away from the observer, right? So all we're going to have to change in our equation, we do FO equal to V plus VO over V minus VS times FS. We go back to our sign conventions, and it says VS is positive when approaching the observer. That's what we did here. It's positive. There's a negative sign in the equation, but this number is positive. We make VS negative when it's moving away from the observer. So here, this car is going away from the observer. It's going that way. So we're going to make VS to be negative. All right. So we have this being 0 again. So we're going to have 340 minus negative 30. I hope that's not too confusing for you all, the way that I've defined these sign conventions. Anyway, so we have 340 over this. Oh, whoops, multiplied by the frequency of the source. So this is equal to 340 divided by 370 times FS was 300. I get 276 hertz, which is going to correspond to, so this is observed frequency. This is going to correspond to an observed wavelength. That'll be 340 over 276. And this is equal to 1.23. I agree. I got the same thing. So there we go. It's getting slightly cut off, but it just says lambda naught. Does anyone have any questions? Okay. So I want you to understand that for me, Astroliver, this is the equation. So for the first part, I'm actually saying VS is positive here, right? And for the second part, I'm saying VS is negative. This is the difference between what I'm doing and what the book's doing. What the book does is it makes this number positive and it uses the opposite sign convention. I find that to be confusing because watch what happens here. Our observed frequency in the first part was bigger. It was 329 than 300, right? In the second part, our observed frequency was 276. It was smaller. So for me, when I look at this equation right here, before doing the calculation, what I think is, if I want the observed frequency to be larger, what has to happen to the denominator? You know what I mean? If I want FO to go up, the denominator needs to get smaller, right? And that's why having a negative sign here, to me, is logical. Because then when the object approaches, you're going to get a bigger frequency. Because you want the denominator to go down. You want the denominator to get smaller. because that'll make the observed frequency bigger. Down here, if the object is going to be moving away, we know from conceptually that the way the Doppler effect works is that when it moves away, we expect the observed frequency to be smaller. The only way that's going to happen is if I make the denominator go up, right? To make the denominator go up, I need to do a negative negative, basically, right here. So we're adding. Yeah, it makes more sense to me too. I also just like, if you look at the book's equation, you try to understand what they're saying, it is really hard to understand the words they use. Personally, I don't understand the words they're using. Okay, anyway, things are always going to be like this though, right? If you learn something one way, you're going to kind of get stuck on it. All right, we have a little bit more time, not much. So I think I might skip this one. This problem, what happens is that it says, if the siren is at rest and the listener is moving away from it at 30 meters per second, what frequency does the listener hear? The only thing that's going to change now is that the observer is the one that's moving now instead of the source. And so what'll happen is, I guess we could go through this kind of relatively quickly. All that's going to happen now is it says what frequency does the listener hear? So if the observer is going towards the source, no, it says if the siren is at rest and the listener is moving away from it. Okay. So now if the listener is moving this way, we'll give him a skateboard. This is velocity of observer, and this is going to be 30. It's actually going to end up being negative, but I'm just going to put that in at the end. And now our siren is sitting still. So Vs is equal to 0. So now F observed is going to be V plus VO over V, because Vs is 0. The term is 0. So I'll put minus 0 times Fs. But when we plug the numbers in, it's going to be 340 minus, we're going to make VO negative. Maybe it makes sense in my definition up here just to call it negative, because it's negative because it's going away from the source. So we put in here 340 minus 30 divided by 340, and then we multiply that by our frequency, which was 300, I think. And now we get the FO equal to, it's going to be 310 over 40. Interesting, you might think that we would get the same answer as when the car was moving away, right? Doesn't that seem reasonable before I put the answer up here? Which one is the same as this? So we could do a relative kind of coordinate change right here and say, well, if this person's moving away at 30 meters per second, that's the same thing as this car moving that direction at 30, but this person's sitting still, right? i.e. this situation. It doesn't look the same, but it would be the same concept, right? But interestingly enough, you get a different answer. We get 274, and it looks really close to the same answer, but it's definitely not the same answer, right? It looks really close to 276, but they're definitely not the same. So interestingly enough, the Doppler effect can kind of distinguish between relative motion where normal motion doesn't. All right, one last problem, which is, we're not going to do this one, even though it's a pretty good problem. We're going to do this problem, because all those other problems are very plug and chug oriented, and this one's not. This one's not from this textbook. I think it's from a different textbook. So, standing at a crosswalk, you hear a frequency of 560 hertz from the siren of an approaching ambulance. After the ambulance passes, the observed frequency of the siren is 480 hertz. We want to determine the ambulance's speed from these observations. All right, so we have a scenario where we have an ambulance, and it's traveling in this direction. Apologize, my horrible drawings. And you're standing here, right? And what you know is that when it's approaching, you hear a frequency of 560. And then when it passes, you hear a frequency, I'm going to call it FO prime. It's equal to 480 hertz. You as the observer is sitting at rest, but the velocity of the source is what we're looking for here. And We'll have to use some velocity for sound. We'll use, I don't know, 343 for sound or something. Let's use that for the velocity of sound. Okay. So how do we figure this out? Well, we can write two different equations. One equation we could write is for the approaching situation, where we say that FO is going to be equal to V plus VO over V minus VS times frequency of source. And then for the for when the ambulance is moving away, we'll put this the receding part. We can write that the observed frequency is going to be equal to V plus VO. And now in the denominator, we're going to write V plus VS. Because in the first part, VS is greater than 0, and the second part, VS is going to be less than 0. But it's the same absolute value, right? Does that make sense how we would have those two different equations there? And then we can say the observer velocity is 0. And I left off one other thing here. These are different. This is FO prime, and that's FO. And I think what we'll do now, probably the easiest thing to do, we don't know what the frequency of the source is, so we want to eliminate that. So basically, we can either solve this equation for Fs and solve this equation for Fs, and then we could plug them into each other if we wanted to. But I always find it easier to just, in situations like this, to just divide these two equations. So on the left-hand side, we're going to have FO over FO prime. We know what these two are. On the right-hand side, we'll have 1 over V minus Vs divided by 1 over V plus Vs. And the Fs's will cancel when we divide the equations. So this is going to lead to an equation that says that FO over FO prime is equal to, we take this denominator and move it to the top, and this will become the denominator. So we have in the denominator V minus Vs, in the numerator V plus Vs. We're trying to solve for the velocity of the source, so we need to kind of do some things with this equation. The first thing we can probably do is just to kind of cross multiply. So we get FO times V minus FO times Vs is equal to FO prime times V plus FO prime times Vs. We're solving for Vs, so I'm going to move this term to the right-hand side and this term back over to the left-hand side. So what we're going to get is FO V minus FO prime V equal to FO prime Vs, and then add this term plus FO Vs. We're solving for Vs, so we're going to factor that out of this side. So we'll have Vs times FO prime plus FO. And the left-hand side, we can simplify a little bit. And solve for Vs. All of this multiplied by V. Plug in the numbers. So FO was 560 and then 480. So it's 560 minus 480 hertz and hertz divided by FO prime is 480 plus 560. And then we have to multiply that times the velocity of sound, which we're going to use 343. Just because that's the velocity of sound at about 20 degrees Celsius. And there we go. I didn't put units on here because everything has hertz, so those units will cancel out. So this is basically how a radar gun works. It takes the change in frequency and it converts it back into a velocity. divide that by 480 plus 560, and then multiply by 343. 26.4 is what I get. Do you all agree? That's about 50 miles an hour. That's a pretty reasonable number. Maybe a little bit more. Dal, I didn't get a chance to answer your question. We're just out of time. So, right here? It's right here. I answered that question. Didn't get to answer your question about what happens when you travel faster than the speed of sound, but I'll try to talk about it a little bit after we get off here and point you to where you can read about it. That's all we have. Okay, you have an exam, right? And so let's talk a little bit about what's going to be on the final. The final is going to cover everything we've studied this semester. So that goes back to the chapters on fluids where we talked about, the Bernoulli effect, things like this. It goes back to stuff about heat transfer, specific heat, calorimetry, stuff like that, ideal gas law, all the stuff about heat engines and the first law and second law of thermodynamics, entropy, and then all the stuff we've been doing recently, mechanical waves and sound waves. So probably what you can expect on the final is I'm going to give you 6 total questions. Those questions will definitely contain at least 2 questions from these last 2 chapters. So there'll be some kind of question on mechanical waves, probably something to do with like standing waves or a traveling wave. Most likely standing waves is probably what I'm going to do for that problem. And it'll probably involve like stringed instruments. And then there'll also be some questions about sound. So those could include problems with Doppler effect, decibels, like we talked about today, but also stuff about just the pressure of a sound wave. And that's pretty much it. So that's what the final is going to cover. As long as you can solve all of the homework problems on mastering physics, you should be fine. If there's any that you can't, that's probably not a big deal either, because there's going to be 6 problems and you only have to answer 4. So just make sure you understand 66% of the material and you're good. No, really, you just need to redo your homework problems mostly. That's what you should focus on. Redo mastering physics problems. Only focus on that. Make sure you can do all of them without a book, without help, and you should be fine. Anyway, that's the end of the lecture. I'm going to stop there. If you all do have other questions, I will stick around and answer them.